what we just saw.
So when you have a water wave, like the bug making a wave in the water, or you have a sound wave, like my voice traveling to your ear, do I move the air from my mouth to your ear? Do I move the water that was under the bug way out till the wave basically dissipates? No.
It vibrates.
So you remember at the beginning, our definition was that energy is what's moving. The wave really, it moves through the media, but it doesn't move the medium.
Well, it kind of, but it records
Just it's,
back.
yeah, right. Because when the air molecule here collides with this one here, then it transfers that energy here to here to here. But the molecules really don't, yes, they just move. They oscillate a tiny bit, but they don't net move. They just oscillate. And that can be kind of a confusing thing about waves. So here I have 3 rubber bands, and they play 3 different pitches. So when I pluck at them, what do they do to cause sound? They vibrate. And so the sound wave that comes from them, let's say they are oscillating this way. Which way does the sound wave go? Right? It'll go out parallel to the oscillation. So if they're oscillating this way, they travel that way, right? They spread out in all directions, essentially. But they travel in the direction of the oscillation. So when they eventually reach my ear, what will determine which rubber band has the highest pitch?
The frequency.
The frequency. So big frequency equals high pitch. So what do you predict? Like if you poke at these 3, Jenna, which one would you think is going to have the highest pitch? Poke them. The thinner one. You can't test it. You can just poke. Up. So yeah. So what is different about the rubber bands that give the difference in pitch? So that's what I kind of thought. That's why I picked 3 different thicknesses and different.
It's like a
everything
guitar.
rubber band.
You know how the thinner strings are higher than the bigger strings?
No, it's the tightness.
Okay,
It's true. It is a tightness.
that's where it comes down, and that is something that is not intuitive because guitar strings, the higher pitched strings are thinner and the lower pitched strings are thicker, but it is the tightness. So if you poke down on these, you can predict which one's going to be the higher pitch by which one just doesn't compress as much, which one's the tightest, right? So this one should be the highest pitch because it feels the tightest to me. This one's much lower. And I can't keep that one on the beaker. But you can pass it around and play with it while I'm talking just to see what you think about tightness. Like a tighter string will vibrate faster, right? And it'll have a higher pitch because the vibration is faster. So the frequency is more. More waves per second are going to hit your hand. So you feel the tightness of the strings, observe them, pluck at them, and we'll keep on moving, although I have no idea where I put everything. Okay, so.
Does this need the camera?
I think it's currently filming. I'm not sure, I hope it is. On the test, you're going to meet with things about the speed of sound, math problems with the equations I put up there. You're also going to meet with Doppler effect problems and then the only few other concepts are the concept of waves that we can hear. So if human hearing range includes the wave, it's called what kind of wave? Sonic wave. If the wave has a lower frequency than we can hear, then it is
Infrasonic.
what?
Infrasonic.
Okay, I'm thinking of something else. And when the wave has a higher frequency than we can hear, ultrasonic. Okay, so what is the range of sound waves that humans can actually hear?
20 hertz to 20,000.
All right, so 20 hertz to 20,000 hertz. And that's really essentially all you need to know. If you find the frequency of a wave, and it's in this range, it'll be a sonic wave. If it's smaller than 20, it'll be infrasonic. If it's larger than 20,000, it'll be ultrasonic. Joshua.
Is 20,000 hertz the breaking point of the eardrum?
I think it probably varies from person to person. I think
Isn't
it's-
that's when
There
it
was a
starts to
graph
damage?
because
Oh.
think of a dog whistle.
That's
A dog whistle. What dogs can hear up to about 40,000 hertz. So you just make a dog whistle of an ultrasonic frequency above 20,000 hertz, and the dog can hear it, but we can't. But it doesn't hurt our eardrum. So what does break your eardrum if it's not frequency?
What did you say?
Amplitude. Amplitude. The amplitude of the sound is what will break your eardrum. So it doesn't matter the pitch so much as the amplitude if it just pushes your eardrums further in than what it can stand. Like holding a Kleenex tight, you can push it so much, but eventually you'll poke right through it. Duchesne?
Can some people hear more than 20,000?
Yes, there is a range of what humans can hear.
Okay.
And you tend to lose, like when you're losing hearing, you tend to lose on the ends. You tend to lose your high range first.
So some people can hear less than 20 hertz
Oh,
also. Okay.
But not much.
Some people have really sensitive hearing.
Yes. And some people, like my mother got hit by lightning when she was 11, and she lost a large amount of the upper end. So she didn't hear high pitches well. And really she didn't hear much, but she read lips really well, so nobody could really tell a whole lot. And she could catch you saying something rude at 100 yards easily, because she could read your lips.
That's cool.
Yeah, it was great. She was a middle school principal, so it was a
Oh, your mom is a school principal?
Yeah. So yeah. The other thing you'll need to know about is Mach speeds. So just how much faster or slower is the speed of a thing compared to the speed of sound. So if a jet's going Mach 2, it's going
2 times.
2 times the speed of sound. And of course, air temperature plays in. You have to know what the air temperature is so that you know what the speed of sound is, so you can tell how much faster or slower something is than the speed of sound. So they just use Mach to kind of tell how much faster than sound something is going. What's my time frame? How much more can we fit into this period?
You have 45 minutes.
Oh, so no,
I'm sorry,
and
less
stay
than
with the
30,
rate.
35.
Like 35 minutes. So that would have been the time it took us to do an experiment, but it's raining. So that's a big bummer. So let's consider what we should actually do. Let's go over the study guide while we think, and then
Could we do like what happens at like the main entrance, like
we should
this
look
end,
at
and then
Yeah, these are whole
I know what we'll do. I'll make up data, and we'll do the lab with made up data.
Yay!
Okay, well, you guys will be done with it.
I mean, it's a bummer, but truly, it is very difficult. Even if we could get as far apart on church property as possible, it's going to be very difficult to do this lab because your reaction time is essentially equal to the time that from when you see it to when you hear it. So there's just so much error with that. So let's think about what we would get. So we'll make up data and do a lab. All right.
Yeah, it's not gonna stop raining anytime
No,
soon.
and it's raining too hard for people and their phones both.
We're gonna
At least
break
those
it.
of us that don't
Our
want
new
to look
phones.
wet when we meet new parents at Tutor Talk.
I mean, I could break
Max.
Oh, your speaker is still on.
No. Not good, probably. Thank you. Okay, so we've got,
Alright.
What question are we on?
Where's my eyes? Can you turn around?
Why should
I can't see.
all right, so here are our times.
you add them all up and then divide it by the number of times?
Yes, so everyone take out a calculator and a piece of paper and find the average time. And that would be from when you saw it to when you heard it, if we actually got to do the lab without rain. I have no idea if those times are any good
Where is
at
it?
all.
the average, well, less than a second, so.
Yes, I suspect they should be a good bit less than that. But
Is it times, Brad? You add all together and then you divide it by.
this, I don't know, it's one of the labs in the book, 14 point something. He probably has a code of kind of weird labs in this module.
Do we have eye protection? We need eye protection. Or we just have this
Your
up here
eyeball
with
is
the pencil.
absolutely no risk from sonic waves at all.
This is the answer.
I'm so on.
Bethany's like, I can find a way.
I can't do that. I'm so sorry.
Well, yeah,
What did you do?
if you know you have like fireworks explode right next to you, you have to hate damage.
I mean,
That's
because
what
might be a
Why did you
crack,
get-
not your eyes.
Yeah.
Yeah, that's what I got.
I have for my siblings do it. They use Roman candles and shoot at each other.
I don't know. That's something's wrong. Awesome.
Gotta add.
I gotta try that.
I did.
I lost count.
What time I couldn't put my hands on it.
Yeah, that's what I did.
Well, you guys are all feeling it.
You rolled? I thought it was Alright, 30 seconds to get an answer. No,
Is that yours?
Yeah, that's it. We must have got it. That's from
Exactly. You're right.
Yeah, if you, when you're averaging, if you get an answer that's
Yeah, I
not
must've-
somewhere in a range, you're probably wrong. So you can just quick check yourself before you just get it wrong.
I got-
So who has an answer? What do we have?
About 0.53 seconds.
Okay, and that's good. And I'll tell you that if your stopwatch, when you're collecting data, gives you out to the hundredth place, for example, you should always keep to the hundredth place, even if your calculator gives you like infinite numbers. You guys don't worry about significant figures, but Maddie does.
Kind of torture.
Yeah, but once you get the hang of it, it'll be okay. But that's one thing to know is whatever thing you use to measure your data, if it goes to the hundredth place, keep to the hundredth place. If it goes to the 10th place, you have to round to the 10th place when you average. So if we have this, and let's say the distance between me and you when you observe this, the sight of the hand clap versus the time you heard the hand clap, let's say the distance was 1/2 kilometer. So how would I convert 1/2 kilometer to meters? Because we really want meters per second. Just remember, like, module 1 here.
You'll multiply the 50 kilometers by 1. Hold on, what are we trying to find?
Like trying to convert it into meters.
So how many meters are in a kilometer?
1,000.
So that'll be
500 meters.
that's correct.
It'd be 5 meters, right?
All right, so 1/2 kilometer or 500 meters, and 0.53 seconds. So, then how will you find the speed? Speed is going to have
You
what
would
unit?
multiply the seconds for the meters.
So distance is rate times time or speed times time, right? So we'll just rearrange that to solve it for speed or velocity.
Distance.
So then we just plug in distance, 500 meters, divided by time, 0.53 seconds. And everyone take 30 seconds to solve for that. Oh, why did I write the answer on the board?
9:45.
Joshua?
It's 943.4
Okay.
meters per second.
And I'm only going to keep, really I should only keep 940 meters per second. So, since I picked the time and I picked the distance and we didn't actually experimentally try this, we'll see what kind of thing I should have picked, Duchesne.
Never mind.
All right, so what is the actual speed of sound in air? Like, how would I calculate it? What's the equation, Max?
It's 331.5 plus 0.6 times the time and meters
Temperature?
times the temperature, sorry, and then meters per second
So
equals.
can anyone solve that for the temperature the air would have to be for my data to be any good? Because it's ridiculous, obviously. So solve for temperature here. Right,
So get
so
meters per second.
you will get, you should just get Celsius. Their units don't work.
So like if we're trying to solve a T, do we just like ignore the meters per second? That's like algebra.
Well, they'll cancel. Well, no, they won't cancel. Yes, this equation doesn't give you units properly. It just is like pretend unit equation. I don't know why they do that, but.
No, it's not.
So if I undo that, I subtract that from both sides.
If I don't bring my lecture,
Yeah, exactly.
Wow.
it's not a good thing
And
to
that's
do.
all I'm saying.
So maybe I should have picked some different
I hate when
numbers.
people just go on and on. I'll just sit
I
there
got
and be like, yep.
102
I say
degrees.
okay. Or I'll say,
Actually, I get 1,020 degrees. Yeah.
It would be different.
that's right. People are swimming or like going on and on and on. It's like,
Alright, so now
I don't think we
you're
were
like, are you mad?
No,
Like measurements.
that would be a bad lab for us. So clearly our time should have been faster than that. And really our reflexes aren't any better than that.
that is really hot.
Right, so I picked bad data, but we picked it and we kind of fooled with it and we can see what the outcome is. Sound isn't nearly that fast, so I should have picked different data, right?
That's really fast too. 914
Right.
meters per second.
So like,
How did we get 1019 degrees Celsius?
Because
I solved for T. So I subtracted this by, so I divided by that.
What in the world?
That's what I did, but I got something completely different.
Why is she showing it to you?
Yeah, you got the right answer with the wrong decimal place, so I think we just didn't put your decimal.
I got 1, 2,
Divided by, yeah, that should come out right.
I got
So, I mean, that's essentially what the lab would do. What we would have actually done, once we found the answer to the speed of sound, right, our 943 meters per second, we hopefully would have found like 300 meters per second. Then we could have used the current air temperature to figure out what the speed of sound should have been and see how close we were. So,
this is the actual equation. Like the answer we got, like 1019.16.
yeah, if the data had been true, the air temperature would have been that. So
we're on, I don't know, Mercury or Mars or something.
yes, a planet receiving a lot of insolation, right? So if we look at the weather right now, I'll tell you what the current air temperature is supposed to be
Even Venus isn't that hot.
outside. So it says it's 63 degrees outside. That's Fahrenheit. Did you guys learn to convert to Celsius? I don't know.
It says